So our next speaker will be remote over Zoom. We'll be showing right now. It'll be Anima Anand Kumar from Caltech. Can you hear us?
Yeah, can you hear me?
Yes, we can hear you.
Okay, great. So can get started?
Yes, please go ahead.
Yeah, thank you for having me talk at this really, I think, important event in bringing focus to what are ways to think about foundation models for science. I'm sorry I couldn't be there in person, but I see the schedule and all the wonderful speakers there. So I think there's a lot that'll be covered. So the perspective that I want to give today is to think of foundation model from the perspective of what is the way to simulate a very diverse set of scientific processes, right? So how do we go about accurately capturing the complexities of many phenomena that we see? And that can be all the way from molecular levels or atomic levels to planetary scales. So you can think of molecular dynamics here. This is actually the spike protein of coronavirus with the protein in our body and how they bind together in a work we did with Argonne Lab. And I know, Arvind Ramanathan is there, and he's our collaborator who produced this beautiful visualization. So you can think of those kind of processes, what are the dynamics that happen when proteins bind with each other or with other molecules. Can also think about the processes that happen at the planetary scale, including clouds moving. What you see here in the visualization are atmospheric rivers that are thousands of miles wide. And indeed, how that develops and what can we forecast about them. So, with all of this, right, there is some amount of data, but certainly not of the level that is available on the internet when it comes to image and text models. And since these are time series, you can naively think of them as video prediction. But there are a number of differences, right, when it comes to standard video prediction versus spatiotemporal prediction that we see in these processes. So most important of them all is that the data is much more limited compared to what we may have on YouTube or other sources of video data. But we do have mathematical equations. We know a lot about these processes than just data alone. When it comes to molecular dynamics, we can model them in terms of Newtonian mechanics, but we could also go further, deeper, and model the quantum mechanics. And we have equations for all of them. And same with the weather on this planet, we can do the Navier-Stokes for fluid dynamics and so on. And sorry, that's how it's been done for all of these decades, right? So there's so much development that has happened in science through HPC, through the development of computational tools to do large-scale simulations. But what can AI do in augmenting or even replacing some of the current simulation methods, and how can it do it better? That's what we want to think about. And to me, that would be a foundation model for science, because it's one that ideally would be able to simulate all kinds of these different processes, right? So very few people will think that this molecules on the left has anything in common to do with the weather of this planet. But indeed, there's a lot of common abstractions. You can think of them in terms of partial differential equations, and you can also think of them in terms of having multiple scales of interactions and behavior. And so that's why there is a lot more in common across different scientific domains than we typically think of. And the common unifying theme is there's mathematical models, there is, right, constraints in physics, And in terms of equations or other conservation laws, there are symmetries. So we can incorporate a common abstraction to model them, and ideally a common model that would be able to simulate all of these different processes. And I think by now you're convinced that text would not be the right modality to model this, right? These are the details of the very processes themselves, not just the textual knowledge of what those interactions look like. And so what is the challenge? Indeed, as I mentioned, there is extensive work on numerical methods for solving partial differential equations, and that is the workhorse of scientific computing. But it is extremely expensive, right? So right now, if you think of standard numerical methods, there is nothing learned, right? It is numerical iterations of trying to solve and arrive at the solution of PDEs. But as you require solutions for very complex processes, for instance, cloud turbulence. So you really need to understand how the clouds move and model their movements. That is turbulent behavior. And for that, you need to get to very fine resolutions. And that's where it gets very expensive. In fact, this is a paper by my colleague Tapio Schneider, where he estimates that it can be really just completely out of reach from the perspective of current computing capabilities, as much as 100 billion times more computing requirements than what we have on the planet today. So, there are the ideal models we want to get to and the ideal level of fidelity in terms of accurately capturing the real world processes, but it is just too expensive. And so that's why we currently limit our models to much coarser resolutions and cannot capture all of the phenomena that are happening on this planet today. So what can AI do here? To me, AI can have the potential to learn better features than what you're assuming for your numerical method, right? So I see the same evolution as we've seen in computer vision, right? And back in 2010, which seems eons ago, right? So researchers were focused on hand engineering features, thinking for computer vision, what would be good features to get us good accuracy. And similarly, in numerical methods, there's tons of work done to come up with what is the right basis for different domains. For instance, for fluid dynamics, maybe pseudospectral solvers work well in a certain regime. For wave propagation, in certain regimes, there's Helmholtz. So there is all this design of specific basis in which the numerical methods iterate in order to solve the problem. But instead of that, why not let machine learning guide us and come up with better feature transformations? And that's what we've seen in a number of domains, that machine learning can now learn nonlinear transformations and solve them much more efficiently. So you can think of now, instead of requiring a very fine grid, if you do it in the ambient domain, by transforming it through nonlinear features into a latent space, you could potentially get away with a much coarser grid and computationally much less expensive. And that's what we see over and over again in many of the problems. And that to me is the main promise of machine learning. Because there has been more than 2 decades of work trying to bring standard numerical solvers to GPUs. And indeed, in some cases, there has been good benefits, but usually they top out at, right, 2 times or 5 times, right? So there's some speed up, but not a lot. And that's because the numerical methods are iterative. And with deep learning, what we see is you only need like a few layers in your neural architecture. If you can think of those as iterations, it's just few iterations, right? Not hundreds or thousands of iterations like you see with numerical solvers. So you get this massive speed up because you can do away with much fewer iterations, and you can run that on the latest GPU with all of the hardware improvements as well. And so we get these massive speedups you will see in many applications that can be from tens of thousands of times to even 1,000,000 times in some regimes. And to me, then the question is, what are the right principled approaches to design deep learning methods for partial differential equations? And indeed, I mentioned, as a first order, you can think of this as a video, right? So it's spatiotemporal. I can take my favorite neural network. I can take a transformer. I can take a U-Net. I can learn on some training data and ask for prediction. But the main challenge is with these kind of physical phenomena, you need to get to the finer scales. So for instance, if I train my fluid dynamics on data that is of limited resolution, let's say only coarse resolution data is available during training, and then at test time, I'm asking to do predictions at a much higher resolution. In a standard neural network, first of all, this is not possible. If you take a U-Net, if you take a transformer, for instance, in transformer, there is patching, and that's on a fixed size. So you assume the inputs and outputs sort of a fixed resolution in a standard neural network. And on top of it, you could add an interpolation like bilinear interpolation, for instance, but that is not going to be that accurate in extending to higher resolutions because that is not data driven, right? So you're putting some interpolation on top that really is not adaptive to the domain. And that's what we see on the plot on the right here, where you see the red curve is taking the U-Net that is trained on a limited resolution. So this dotted line is the resolution that is seen only during training on the left, and on the right are higher resolutions that are not seen during training. So we are demanding a zero-shot super resolution, which is a hard task because the model isn't trained for this higher resolution predictions. But you can see that indeed, U-Net with a bilinear interpolation, which is the red curve here, does pretty poorly. It does not capture the finer scales very well. On the other hand, the neural operator, which we've designed, can accurately capture the trend. So you can see that it can also extrapolate and get to this higher resolution prediction pretty accurately, even though it has never seen that during training. Of course, this sounds like magic. You've not seen something during training. How can you expect to do well? Right? So there are different aspects, and I will get into it in a bit, but mainly it's a combination of the model, first of all, having the capacity to model continuous phenomena. So it's not just now limited to one resolution or one fixed dimension, but the input and output can be at any resolution. So you can, at test time, input any resolution without having to retrain. And the second one is nice inductive bias that does make this extrapolation graceful and pretty accurate. And there is extensive library development here in GitHub that I'm showing, where we have lots of open source code, a very thriving community. So I encourage you to go check that out as well. So how can we close the gap here? So in the blue curve, you see, if you've trained on only limited resolution data, you can get pretty close to the ground truth when you're looking at finer resolutions, but you can never be perfect, right? Because it's never seen that data, so you cannot overcome that approximation error. On the other hand, we have constraints from physics, and that's the unique aspects about scientific machine learning as opposed to standard image or video models. And we want to incorporate that. And that's what we did with physics-informed setting, where once we include the physics constraints as loss functions over these equations, these Navier-Stokes equations, we can close the gap and in fact get nearly perfect reconstruction even at a higher resolution. So think of it as you have data at a coarse resolution, and now you can add the constraints of physics at a finer resolution all into one model, because neural operators can function at multiple resolutions and take in training data and do testing at multiple resolutions. So you combine coarse resolution loss function corresponding to data with a finer resolution loss function corresponding to the PDE constraints. And combining both of them, you can now essentially extract information from both the data and the physics to get to a high fidelity solver. So let me show you some applications, and if there's time, I can delve into some of the methods as well. So in terms of applications, I would say that our ForecastNet for weather forecasting is one of really good success stories. We were the first to build a high resolution AI-based weather model that is not only tens of thousands of times faster than current numerical weather models, but also in many cases as accurate or even more accurate. So what you see is that it's running in ECMWF. So you can go to ECMWF, which is the European Center for Medium Range Weather Forecasts, and the model is running. So you can get the weather forecast for the next 2 weeks by going and querying the model, looking at the charts. It's also open source. So the model weights are freely available. The code for training is available. And yeah, it's Apache license. So we really want to, you have the community use it, commercial entities use it. That's how we had our mission to help democratize weather forecasting. So to me, the speed up really right now shows the democratization going from a large CPU-based supercomputer to do traditional weather forecast to actually just a gaming GPU that you can run at your home. And in fact, this is something that a lot of people are just doing with very limited resources because we've given out the pre-trained model. So as I mentioned, there are cases where we can do pretty well in terms of deterministic forecasts, like being able to predict the weather for the next 2 weeks. But this is also important for chaotic events like extreme weather, like hurricanes. With the hurricane, the challenge is it's chaotic, meaning you can somewhat predict where the hurricane will go, but not too early, right? Because, a week or 2 weeks before the hurricane happens, it could go anywhere. And what you need there is not just one deterministic forecast, but actually an ensemble, meaning you perturb the initial conditions and you look at different trajectories and come up with probability of these extreme events. So this is very challenging for traditional models because these are tail probabilities, right? And what we know is if you have just few samples, you do not get good tail probabilities. And because of the enormous cost of current weather models, in fact, you'll be surprised that current weather agencies just use 50 ensembles, meaning if you took an average of 50 numbers, we know, right, the error bars are quite large, but we are forced to do it because of the cost. And this is where, there's very interesting ongoing work with our collaborators at the Lawrence Berkeley Lab, where they're showing that you can do these massive ensembles with our AI-based model, and in fact beat the current traditional models in terms of better risk assessment for extreme weather, which is extremely important as climate change is going to bring about more of such events. So it's not only that domain, there's many others, right? From material deformation, nuclear fusion. This is something I posted on social media just yesterday in terms of how we are able to train on the tokamak data and predict disruption before it happens. And in fact, with the magnetohydrodynamic equations, which are very slow with the traditional codes, our models can be 1,000,000 times faster. And other applications like ultrasound, which require real-time reconstruction as well, we can do very fast forward simulation. But it's not just the forward that is good with machine learning, but also the inverse, right? So our ability to have differentiable models because the AI models are automatically differentiable. You can now ask what is the best design parameters based on this forward simulation and directly come up with that. I'm very proud of this catheter that we did as a collaboration at Caltech, where the goal was to reduce one of the biggest sources of healthcare related infections in hospitals. Many of you may be surprised. I certainly did not know that if you are having catheters to patients where the fluid is taken out of the human body, over time, the bacteria tend to swim upstream near the wall where there is slower speed and can infect the human. And so our collaborators had a really elegant, but simple and elegant idea where why not put like these ridges or triangular shapes where we can have the bacteria get like being overcome by vortices. So once they create vortices, the bacteria cannot swim past. And you can see that in this video here, which is done in the lab, where all the bacteria particles are getting pushed out and barely 1 or 2 are trying to swim by the wall. So we were able to obtain 100-fold reduction in bacterial contamination through our AI model that optimized the design. So the AI model learned the fluid flow behavior under different shapes, and we directly, through gradient descent, optimized the shape of the catheter with our AI model. And then we had to 3D print it and test it only once in the lab. And to me, I think that is the biggest potential for the AI-based simulation models, because we can remove this iterative back and forth testing in the lab to a large extent and come up with optimized designs. I know we've done the similar inverse design for optimized masks in lithography that I don't want to get into, but this is a broadly applicable framework. So, so far I talked about models where we trained the model for a specific domain and then looked at very large speedups, sometimes from tens of thousands to 1 million times speed up, as well as being able to do inverse design and inverse problems on that model. But of course, this symposium is about a foundation model. So what would a foundation model for science look like? I mean, to me, a foundation model for science should be able to simulate all kinds of real world and artificial phenomena that we require for science and engineering. And that's where one that is built on a variety of different partial differential equations and other mathematical models that we know for different scenarios can be one that can be broadly useful. And so we've created one such model that is in fact the largest in terms of its diversity and the number of parameters in the model with state-of-the-art performance, where you're looking at now this very diverse data, right? There can be 3D data, there can be an irregular mesh. So it's much more diverse than a standard foundation model you may think for vision. And I think to me, these aspects where we've shown our model even outperform some of the narrowly trained models. So we are seeing this emergence at scale that you've seen with language models now for PDEs as well. And here there's different kinds of generalizations. Of course, I can train on different partial differential equations, and at test time, I can give new conditions, right? New regimes. For instance, I could change the Reynolds number of fluid dynamics, see how well it does at test time. So this different kinds of zero-shot generalizations. But there's also one of increasing complexity. So what language models are good at are compositionality. You can ideally train it on simple concepts, and hopefully in some cases it composes and makes also more difficult and complex combinations of those. And another recent work of ours, we wanted to test that by asking, what if we train our model extensively on single physics, meaning a single partial differential equation like fluid dynamics or elastic waves. And then at test time, we fine-tune on just a few examples of multiphysics where these equations are coupled, and then see that it can generalize much more easily rather than having to have lots of data on multiphysics scenarios. And I think this is another kind of generalization that you typically don't see a lot of that kind of discussion with standard, text or image models. But here it's essential because science is built on simple phenomena, right, leading to more complex compositions and couplings, and one that can be captured through, like in standard numerical solvers, which is much more challenging to solve. And if deep learning models can give us a big boost, I think that would be world changing. And so this is where I see that the future lies, that we can bring in the principled approach of neural operator for having the expressivity to model the solution operator of partial differential equations and other multi-scale scientific phenomena. And then with the right architectural and design choices, really scale it up to capture a wide range of domains. So I just wanted to see how much time I had, and if not, I'm also happy to stop here and take questions.
You have about 2-3 more minutes if you want it. Otherwise, we can take questions.
Okay. So if I have just 2-3 minutes, all I want to show is a little bit more in depth what are neural operators, right? We kind of didn't really delve into it. I know I don't have a lot of time. But really the difference, as I mentioned in the beginning, is think of neural networks where the input and output are fixed to one resolution, and neural operators are where there is flexibility to change the resolution. And that's really the primary difference. So neural operators, think of them as a superset of neural networks. And of course, the specific architecture is a detail, but it's really this broad class, which allows you to now query at any resolution. So one way to think about this is you can think of raster graphics versus vector graphics. In vector graphics, you can keep zooming in and it still retains the shape, whereas with raster graphics here, right, if you have limited pixels, it just gets blurry. And that's really the difference, because we are making our neural operators to output functions and not just vectors or objects of fixed dimension. And the other way to show that is, you can think of like now one-dimensional time series, right? So the input is a time series where you've sampled at these fixed grid points, and the output is also another time series only sampled at those fixed grid points. So if you're trying to use a standard neural network, it only learns to predict what happens at these fixed times and nothing in between, right? It doesn't bother what happens in between the discretizations that is given to the model. On the other hand, the neural operator learns the mapping between treating the input as a function, the output as a function as well. So it tries to, continue both of those discrete points into functions and learns the mapping between them. And by doing that, we can now talk about super resolution, because you can say, now tell me what is the solution at some intermediate point, right? So I can do that without needing to have trained on those intermediate points. So in a way, it's both learning the mapping between input and output, and at the same time learning to interpolate in between the grid points which are not seen during training. So it's simultaneously trying to do both in a neural operator model. And I won't get into the details here. There's a whole range of architectures. You can do it in the Fourier domain. You can do it in the graph-based architectures, and you can relate them in terms of numerical methods as a special case of these neural operators. And so that's why, in a way, we are building from the principles of numerical methods, which have nice convergence guarantees, nice approximation guarantees. But we are also making that richer because we are adding nonlinear transformations that are missing in the numerical method. So that's another way to think of approaching this. And for irregular geometries as well, we can adapt them. And the nice property of neural operators, right? This is really the key, because the way we construct these methods, it guarantees that, if you train the model and at test time you give it different resolutions, there's a nice consistency. So this is what we call like discretization invariance in the limit of mesh refinement. As long as your mesh is sufficiently refined or sufficiently dense, you have a nice consistency property where just making the mesh a bit denser doesn't completely throw off the solution, right? It's converging to a nice limit to the actual, hopefully the underlying function. And that's the nice guarantee that we have, which isn't true if you're taking a standard neural network, right? So you don't have that nice guarantee of consistency as you make your grid points closer and closer, and you have this guarantee that it converges to a unique limit. So
Okay.
I think that
Thank
would
you.
be...
I think we have to stop here. Thank you so much, Professor Anand Kumar. So we have time for a couple questions. Maybe I'll start with one. Can you talk a little bit about training data and generalization, particularly with respect to, for example, geometry, because the solutions are not just a function of the equations, but also the geometries. Have you done much work to see what kind of training data you need to generalize across a little bit more general domains?
Yeah, and this is where, I didn't get into the details, but like models like this, where you can think of like irregular geometry as a deformation of a regular latent grid. And by learning these transformations, you can nicely generalize across geometries as well. Of course, in training time, we need some diversity of geometries, but it does nicely extend to new unknown geometries. That's how in the catheter example, we were able to optimize the design, right? It didn't see that specific shape during training. We've seen that in this example for cars with like the wings, the airfoils. So number of cases where a material deformation where in fact the geometry is changing over time. So it can capture that because we treat the learning in terms of there is irregular geometry, but there's a deformation to a regular grid in the latent space.
Thank you. We have time for one very quick question and answer while the next speaker sets up.
Hi, Professor. Very interesting talk. So I have a question relevant to a previous talk today given by Michael. So I think one very interesting comment you made is that those like large language model or foundation models have a special property, which is like compositionality. And you think like by pre-training on multiple physics can probably generalize better due to this property. I wonder if this is like model architecture agnostic. So say, will FNO have this compositionality? Would like graph neural operator have this, or like transformer? Is it like specific to a structure or architecture, or it's probably generalizable? Have you ever thought about that?
Yeah, I mean, to me, those are two separate aspects, right? You do want an expressive architecture as well as a good inductive bias, right? So you need to balance that. I mean, to me, as I mentioned, the neural operator is the concept of being able to directly generalize to any resolution, right? And that can be based on transformer. We, in fact, have some, like the channel side as a transformer in one of the papers that we recently posted. So there are lots of architectural details that you can dive into. And for instance, if you make the graph too local, it's not expressive, right? So it cannot be a good foundation model by itself. You need a model that can capture both local and global properties well. And also there's much less data than internet scale data for language or vision. So we also need to be careful in putting a very general purpose transformer, which may not have enough data. So having some structure, I think helps. And that's what we saw, in fact, in a recent paper, the transformer attention doing it in the Fourier domain became a lot more efficient and scalable. So I think it needs to be more thoughtful, and we can bring in the lessons from language and vision, but many times we need to do a bit more work.
All right, well, let's thank Professor Anand Kumar one more time.
Thank you, everyone.